I should be live. Let me quickly refresh Twitch. Okay, perfect. Hello again, everyone. Welcome back to more of the compiler project. Sorry for last week. I was way too sick to be able to stream, but I'm finally doing better, so let's get back into it. A quick update that I forgot to mention last time, Twitch is pretty bad at keeping previous broadcasts. It deletes them after like 2 weeks or something. And is also starting to enforce pretty strong restrictions on the amount of videos that can be stored. So I created a second YouTube channel on which I have started uploading all of the previous broadcasts for archival purposes, basically. With no post-processing, no subtitles, just like a raw dump of the broadcast, just to have them stored somewhere. The only thing is I'm missing 2 broadcasts. I'm missing the very first one, which anyway didn't work because I had the hardware issues, which is not a big deal. And I'm missing the one from the 1st of April, which is the day we found the bug in Alex. So that's a bit of a shame. But otherwise, everything else, I've managed to get a copy before Twitch deleted the past broadcast. So I'll be uploading everything to the second channel. And I'll put the link somewhere, probably on the GitHub page of the project. For this evening, last time we finished the linker, as in we have a bunch of bytecode for a bunch of different functions. We need to assign a unique address to each of them, which was not too complicated. And we did most of the work for the assembler, as in, okay, we have the bunch of resolved bytecode. How do we make that into an image? The last thing we're missing is to put that together, finish making the assembly. We have the image for each function. How do we create the big image that results from all of this? So that's what we're going to tackle this evening. I don't know how long that's going to take. If we have time, there's another thing I would like to do. I would like to change the way templates are loaded, because I have a bunch of very similar things here, and having a bunch of similar things where the only thing that changes is a string is error prone, and some of the bugs we had last week was caused by a string here being wrong. So I'd like to use template Haskell to generate this for me, perhaps, if we have time. So yeah, let's get started. I'll go back there. So last time we finished this generate function image function that, given a list of instructions, our bytecode generates a corresponding image. And we were trying it. So for instance, entrance, push int, subtract branch, subtract return gives us this piece of Piètre code. You can see the entrance into the function here, the series of instructions represented by the color changes, and the 2 things, the branch and the return at the end. Now the question is, how do we compose all of those images into one big function? And for that, we're going to need to basically decide what the size of the overall image should be based on the size of the images we have so far, and then append them on that base image. And the last thing we need to do is, if I drag this back, which is the logo of the project, which is not exactly how we're doing things, because this one was crafted manually, but it is an inspiration. The last thing we need to do is we need to do the strip here, which is the one that does the go-to mechanism of our program, basically. So let's do that. So here, our assemble function is going to be given a series of images that correspond to the different functions, and an int, which, if I remember correctly, is the number of entrances in a given function, which is something we need to generate the proper image. Why do we use the index? I do not remember that. Okay, so we generate the image for each function. We zip with the index, and I don't remember why we wanted the index. Is it because we need to remember? Probably because we need to remember the. No, actually, it's probably not that. Why do we need the index? Oh, I guess just because we need to know the offset, and it's easier to just recompute the offset every time rather than like pass a accumulator for everything. Yeah, okay. That should be it. And then we just need to add function for each function. So we need to define what the initial image is, and then what adding a function means. So the max height we have decided is the maximum of the number of rows of each image. So if a function is 10 pixels long, we're saying 10. That's incorrect. We need more buffer than that. So above the function, the entrance, we only need one, given the way entrances, like they have this white bar here. But we need 1 pixel above, we need 1 pixel below, because the control flow will flow around the function. And we need one separation, so 3 plus the amount required for the strip, which is the number of entrances in the function, plus 1. So that's the size of the maximum function plus maximum number of entries into a given function plus 4. So that's the maximum of the size of the images plus maximum of map first of images plus, again, we said 1 below, 2 above, and 1 above still. So that's plus 4. So that's the image height. And for the width, it's just 10 for each function, which is 1, 2, 3, 6, and 1, 10. And we just need, I think we just need one more there, but 2 more would be nice, I think. Yeah, that's exactly what we have. Okay, perfect. Okay, so our initial image is going to be an image made of a canvas, which is this size, plus a starter thing here. And whenever we add a function, we'll just have to add the corresponding strip here, which is something that we're not gonna be able to use our templates for. We're gonna have to generate manually, I think. No, actually, we're gonna be able. No, we can use a template for it, I think. Okay, let's get started. I don't remember the way the library we're using for functions for images works, but that's fine. Because we just need to create an empty image of the right size. And I'm pretty certain, yeah, there's a make image, and I could just say, like, regardless, the function always returns a white pixel or something. That's probably the easiest, yeah. Oops. Let's see. Do I have an... No, I don't. Interesting. Ah, there we go. Make image right there. So that's number of rows, number of columns, and then given a row and a column, the pixel value to associate to that particular pixel. So for us, it's just going to be that starting image, which is, hello, how are you? So it's going to be just this function, but with always white, basically. Except we're going to have to also add our template to this. So empty image is going to be make image of which is then gonna say always. I don't know if my microphone is picking it up, but the weather outside is fierce. So that's what it's gonna be. It's gonna be full white on every pixel on the empty image. And the only thing is we're gonna need one more template for the top left corner. So basically for this thing, what this does is it pushes a 1 on the stack, which is going to be the address at which our program starts. So we are going to be using this function address selection thing to go to the first address, which is going to be the start of our main. And it needs, since we are using the side of the image for control flow, it needs here a small thing that pushes a 1 and then does a pointer instruction so that it turns properly to then go into the selection strip there. Come to think of it, will I need... I'm thinking about the way... That should be fine. What I'm thinking about is there's two elements that determine where Pete goes to look for a next instruction. There's the overall direction, and there's a binary switch, which is, do we look at the rightmost pixel of the edge we're looking at or the leftmost pixel of the edge we're looking at? Which means if I were to extend this thing to always be, say, 2-3 pixels, and the next one is 1 pixel, how do I align them so that it always selects the right one? And I need to figure that out, and I don't have... I guess I could make it so that the last pixel here always has black pixels above, which guarantee that the move into the last group always selects the rightmost pixel of the edge so that it always chains properly into the next one. Or the other way around, depending on how I align those things. Okay. Next, so we have the empty image. So let's make a new template for the top left corner. Using our template pseudo language that I don't remember because it was 2 weeks ago. What does that look like? Something like this. I think we're using... I don't remember what we did. That's too long ago. Okay, so 0 is the start color, and then the nickname for each instruction is based on the offset from the start. Okay. So for the corner thing, it's going to be a 0, which is our starting color. It's going to be capital P for a push. And that's it, I think. Because then it's just going to corner the image. However, here below it, we are going to need something here for the pointer that I don't know what it is. And then 0, push. So push a 1 on the stack. And then here a pointer instruction. Pointer is... It is 3 hue changes, 1 darker. And we are already 1 darker than the start, so that's 3 hue 2 dark than the start. And 3 hue 2 dark than the start. That's an S. Okay, so that should be... And then transparent is dots, if I remember correctly. No, it's just... Actually, here we probably want white, just to be sure. Okay, so that's our corner, the beginning of our program. We push a 1 on the stack for the address, and whenever we finish going all around the image and we go back here, we push a 1 to then do a pointer to rotate 90 degrees and then start going this way to go through the function selection instructions. Okay. So now if we go back to the assembly, how did we apply template? Is that from our template function? Apply template, perfect, which is, yes, this is a function I have duplicated from the image library because it was not doing transparency composition correctly. It wasn't doing it the way I would like. I needed. And this is applying. I should probably rewrite this for clarity. Which one is the template? Which one is the base image? I apply the template on the image. So template is the first argument. Okay. So that's the empty image. The initial image is going to be apply template on at 0, 0. The template we're gonna apply is corner template on the empty image, which I guess I could inline since it's never gonna be used for anything else. Okay, there we go. Next. Next, I need to declare the template, which is the part that, again, I'm thinking of redoing with template Haskell just to avoid having a bunch of string stuff here. Okay. Now we have our base image and we have our fold over it using the add function, which is not defined, but is here. So that's our base image. And this is an image as well. What are we going to do here? We're gonna add this image at a specific location, and we then need to add the function selection thing on top, and that's basically it. So this is going to be an append image, append template. No, what did we call it again? Apply template of this function on our base image. The coordinates for this are going to be it's row first and index second. So row is going to be, I will need to carry over. If I need to carry it over, do I want to use some state instead? Because I will need to know a few things, including the maximum number of, Do I want to use that as part of the accumulator, or do I want to do that as a state monad? It might be easier to just do it as part of this, so I need an int here. And if I need anything else, I'll move to an actual state monad. So here in assemble, our fold needs the initial image and something else. And the something else is I'm going to introduce something else here, which is the size of the selection strip thing. So strip height, I guess, which is this. And in our fold, we're going to be giving this so that the functions know where to insert themselves. Okay. Okay, so now we have as well the strip max. Well, no, it's yeah, strip height, I guess. The only downside of this approach is I'm basically gonna just forward it unmodified, which a reader monad or a state monad would be a bit better for this, but that's not the end of the world. So for now, if we just do this without the strip for now, the height at which we add the function is going to be we skip 1 pixel above the strip height, 2 below. So it's going to be at the strip height plus 3. And column wise, it's going to be at 1 plus 10 times the index. Okay, so if we try this, first it doesn't compile, so we need to fix that. Okay, so this fold is unhappy with. Oh, yes, because here this is not what this is. This is an int, which is the index, with an int, which is the number of entrances and the function. Okay. Corner template. Yes, corner template needs an argument, which I'm going to use red for. After all, why not? Okay. Name for index, shadows, something from lens. Okay. Count. Define but not use entrances. That's correct. We're going to need to fix that. And that's all, I think. Okay. So if we go back to our GHCI, so what does so assemble requires? Okay, so we're gonna try to assemble. It requires a list of functions, and each of them is a tuple of number of entrances, which has been extracted before, and the instructions. Let's actually start with function 0, which is a tuple of 1 and the instructions entrance 0 read int. What's the bytecode again? It's in int. What do we do with that? I don't have. Ah, yeah, okay, of course. So I will need to do a. So this has two. I'm trying to basically rewrite the Fibo thing I have in this image, but in bytecode. So that would be we read an integer from the standard input, it goes onto the stack. Then we push an address. Oh, at this point it resolves, so it's just a push int, which is going to be the address of that function, the Fibonacci function, basically. We're going to say, let's say 2. And after that, we have a return, which is just like quit the execution and use that address as the place to go next. Then we have an entrance. And we'll do an out int. And finally, we'll introduce a terminate instruction to stop the execution. Oops, I meant to go here. So that's our function 0. Entrance is applies to too few arguments. Yes. Entrance address of the phase. When we are resolved, the entrance address is unit because there is no longer any need for a entrance info. So there we go. Except here I have, yes, okay. And function 1, which is going to be our Fibo function. What does it do? It's going to have an entrance, of course. Then we are going to do a push int 1 greater. So if the thing is greater than 1, then we need to do something. Otherwise, we need to do something else. If I do a switch at this point, I probably need to do. So if I do a switch, I'll switch if it is greater than 1. Okay, I can do that. So switch. Sorry, branch is the instruction. Actually, no, that's not correct because I need to push the address first if I want to go somewhere. So I would need to do a. That's tricky. Because there's no swap, there's only roll. So I will need to push the address, which is. So greater is correct. Then I need to push the address I'll go to next, which is going to be. Oh, wait. The address is standard 1, so my push int 2 here is incorrect. So it's going to be address 4. Then we need to swap those. I don't remember. It's fine for now because for now we're just testing the image generation part. But if the image if I want to try a correct image, I'll need to check this. Push 1, push 2, which means rotate the 2 top values by 1. Roll so that the condition is above the. So that the condition is above the address. Now I can do a branch. I don't remember if my branch template does a pop of the address. It does not. Okay. Actually, after branch, I don't know if you have the same problem as with entrance. I don't remember how we solved that problem for the entrance, where what matters is not like each instruction cannot be added in isolation. I need a starting pixel of the previous color of something. How did we resolve that for entrance, actually? I don't remember. Okay, so after an entrance and a branch, we always just add an empty instruction so that future instructions have a reference point. Okay. So that works, which means I can do a branch and then, so we'll branch to the next entrance if it was greater than 1. So we're in the case where it's not greater than 1. We can pop. This is not going to be enough. In the main function, I need to push the return address on the stack. I haven't done that. Okay, that's fine. For now, we're just trying to generate an image. It's okay for those functions to be wrong. We'll fix them later. Pop of the address that we no longer need. And in this branch, we're basically going to be pushing a 1 and then return, basically. Except no, we're going to have to actually make sure that this 1 is below the return address, that the return address is on top of the stack. We can do that later. Then second entrance, where we can do the recursive calls to the previous value, which for now we're not going to do. Push 1, subtract. And for now, I'm just going to say return, and we'll figure that out later. Push, those are push int. So those are completely wrong for now, but that's fine. We'll fix that as we go. Entrance here requires a unit. There we go. So now I have function 0, function 1. If I display image of generate, of assemble function 0, function 1, what do I get? Interesting. The base image is transparent, not what I was expecting. Otherwise, that looks fine to me. We do have one thing of margin on all of them. That's good. 2. Okay, I think we're 1. Oh no, we're definitely fine. We might be too low, actually. Oh, actually, okay, the image for the function starts there. So I don't need to take. Okay, so I'm counting too much buffer on top. I don't need to do that, I think. Because the image includes those 2 pixels. Okay. Okay, so that looks pretty decent. Let's fix a few things. Yes, this is all 1s, including transparency. And now, since the functions include the buffer above, this is +2. I can go 2 pixels higher than that. And that means here it is strip height +2. No, +1. Yes, I think that's correct. Let's try again. Ah. Okay, we have 2 pixels here of margin for the strip, which is correct because that's what will be needed because there's only 2 entrances per function. However, it's still a transparent background. I am not sure why. But otherwise, everything else seems okay. So why is it a transparent? Oh, is it because those are in word 8 and not double, and therefore if I want uh, white, I need to use this, which then puts into question where did I get this? Okay, that is, I guess it's technically correct. When I'm saying transparent, I'm saying 1110, which is not what I was expecting, which is 255, 255, 255, 0. But since it's transparency 0 anyway, the actual color doesn't matter. So this doesn't matter. I'm just going to set everything to 0 just for it to avoid having something wrong. And I think here I'm going to use instead this. Let's try again. Function 0, function 1, assemble. Zoom on that. Okay, and now we have perfect. So the only thing missing is having the strip for the image selection, for the function selection on top. Okay. So this is the part that's going to be somewhat tricky. That's fine. I guess I can just do a template for one line. I can do the template for the first line and a second template for the other lines, so I can guarantee that there is always a proper, for this idea of the bit flip, or of do we select the leftmost pixel of the edge or the rightmost pixel of the edge, I can enforce that for the things for which size doesn't matter, it's all black pixels to guarantee that we are correctly aligned. I can do that. Excuse me. So, if I look at this, this is given a starting color. That is not a push. What is this? We're going from red to blue, which is 4 steps in hue, but no change in lightness. That's a duplicate. Okay. Then we push. So that's a 2 here because there are 2 entrances. So we duplicate the current address that we're going to. We push a 2. I'm assuming this is a greater from dark blue to dark yellow. That's 1, 2, 3 changes in hue, but no change. That's a greater. Okay. Then from dark yellow to light cyan, that's 2, 1. No, that can't be right. This is not light cyan, this is regular cyan, so it's 2, 2. That's a not, okay? So we're looking at not greater. And then I assume that this is a pointer, meaning we rotate 90 degrees if we are not greater than 2. So if the address was 1 or 2, we rotate. And otherwise, we push that value and we do a subtraction. Okay. So let's go back to our templates. So this is going to be it's not going to be aligned with the function, so I don't think I need to try to like make it so it's like a bunch of transparency at first. It's not going to be aligned, so that's fine. So this is going to be a starting value, red in this case. Then it's going to be a duplicate. I'm going to put this here so that I can see what I'm doing, which is going to be duplicate is 4 steps and no change in lightness. So that indeed D. Then it is push A. It's going to be a push based on that current one. So it's going to be compared to the starting color. It's going to be 4 change in hue, 1 change in darkness. R. Then it is the greater, which is 3 steps of hue, none of lightness. We are at 4. We had at 4-1, so we become a 7-1. Modulo 6, that's a 1-1, so that's a minus. Then we do. So that was the greater. Now we can do the pointer, which compared to the previous one is +3 +1. We were at +1 +1. We go at 4-2, which is an I. And then, so 1, 2, 3, 4, 5, 6, 7, 8. There's 2 instructions there. Oh, push and subtract. 1, 2, 3, 4, 5, 6 so far. 1, 2, 3. We're missing 1. 3, 4, 5. What are we missing? Because this was start, duplicate, push, greater, not pointer. So we should have start, duplicate, push. We don't have the push, I think. And we have the push. Then greater. Oh, it's a pointer we don't have, right? Let's redo this. So this is the push. We are on 4-1. After this, we need a greater, which is 3 steps and no change in lightness. That's a 7-1, which becomes a 1-1, which is the subtract, which is the minus. Okay. Then we need the not, which is +2 +2. That's the thing we're missing. +2 +2 from minus, that's 3, 3, or also known as 3, 0. So that's this. And then we need the pointer, which is +3 +1. And from 3, 0 +3 +1, that's 6, 1, which is 0, 1, which is this. Okay, so that's the pointer instruction. After that, we need a push, which is just a +1 darkness. So we had this, so that's just an X. And then we need a subtract, which is 1, 1. From where we are at 0, 2. We need to be at 1, 3, which is 1, 0. So that's this. Okay, so that's the base of our strip. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, perfect. And now, how do we extend this for more columns, for more lines than the first one? We are gonna want to, the things that have a value that is relevant for a push need to be extended. The others can be black to guarantee that the execution flows the way we expect. which means which one is the one we need to extend? It is the second one and the pointer there. So this can be dark. Then all of this can just be transparent, and then this needs to be extended, and this like this. Okay. Okay, and with this in place, let's try. Let's go back to assembly. Oh, wait, first the templates. Again, I'm gonna probably do something to generate those automatically afterwards. Okay. So here, in add function, so we're applying the template of the function. We're gonna need to compose. Do I want to rename apply template to just compose something? Or append or something? Because we're not applying templates there, we're just combining other images. I don't know. So here the entrance thing is going to be relevant because we're going to want to iterate over the number of entrances. And we're going to want to add. We always want to add like this number is never going to be less than 1. So we always want to add the base, the strip 0 thing. And then we want to add the other ones as needed. Is there a way to compose if I have a list of functions from A to A? Let's see what Google has to say for this. Oh, let me put it here so it's visible on the screen. If I have a list of functions from A to A, can I combine them as a function from A to A? I don't think there's a monoid instance. Okay, so there isn't anything like this. Would monoid have something like endo or something? Okay, so there is something like this. So if I wrap them in endo, I can do that. So I can concatenate a bunch of functions to apply on the base image. Okay, so this is going to be apply appendo of all transforms on the base image. And all transforms is going to be a list. I guess mconcat all transforms. And that's going to be, oops, let me just check this. Okay. All transforms is going to be a list of all the transformations to apply on our image. And that list is going to contain this apply template at this of the function. It's going to be an apply template at row 1 I could use base column as being, or reference column as being this. So that's reference column because this is where the function starts. And the first line of our strip is not exactly at this, it is at the reference column plus 1, 2, 3, 4, 5. Oh, actually, that means I need more buffer at the end of the image because otherwise the strip for the last function would be truncated. So that means I need 2 more at the end of the image. So the max width plus 4. Okay. So reference column plus 5, and what we're gonna add is it's gonna be the strip 0 template with what base color we want for this. I've been using green for functions. Let's use red for this so I can compare with this image. And then we're gonna need to append those two transformations at the beginning of a generated list of transformations for each. Yep, we're gonna do that. Okay, so this is gonna be concatenated with a list that I'm gonna generate with a do block, and that's gonna be for each index, which is gonna be a value, not index because strip index, which is gonna a function that is gonna be a value that goes from 1 to the number of entrances. Actually, this is inclusive, right? So if I have 1 to 1, it's still gonna contain 1. That's wrong. I want from 2 because I need to skip. I need to skip the first one. I guess I could do 1, 2 entrances minus 1, I guess, or 2 entrances. For that index, we're gonna do pure, and it's gonna be an apply template at the row is gonna be the strip index, basically. Reference column plus 5, that hasn't changed, of strip 1. Okay. That's all the transformations, I think. And of course, no, that's not true. I need to do a map endo on that, so that I can use the monoid property of endo to concatenate all of them as one function from image to image, app endo to get that function, apply it to the base image. Okay. Corner template doesn't exist. Did I remove it by mistake? I might have removed it by mistake. Again, this should be generated. Okay, that compiles at least. So let's try with function 0, function 1 that we had. Okay, that looks wrong. It is off by 1. The colors are correct, I think. The colors are correct. So our template is correct. So we do go here, we enter here. Oh, actually, since we're arriving from something that doesn't have... I think I don't need this to be... Yeah, okay, I'm gonna change this. I'm gonna change this. I need to just make sure that this selection of the correct pointer of, well, not pointer, because of whatever it's called, that allows me to select leftmost edge or leftmost pixel or rightmost pixel. I need to do it at this rotation here rather than doing it here at the entrance. I think that's better. And then I don't have to worry about this at all. That's going to be trivial to do, so let's do that. And that's going to make everything a bit simpler. And I can keep it at the exit block, and that's going to be enough, basically. Okay, so let's do that. Let's fix our off by 1. So all of those are reference con plus 5, let's say plus 4. And let's go back to our template. Corner here. I'm going to add another line here, and this is going to have a black pixel here. So when we do the rotation, we rotate 90 degrees. If the pointer is saying pick the rightmost pixel, it's going to hit the wall. It's going to flip that, and we're going to be in a situation where we pick the leftmost pixel of the edge, going forward for the selection. And since there's never going to be a reason for that to change, then we're going to be going through the right pixel selection process for the entire strip. Which means I can rewrite strip 0 and strip 1. To be basically similar. Except I think it would look nice to not have... I think it would look nice to have the... to have clearly the values that indicate the function size be very visible. So keeping something like this might be better. Okay, let's try that. So here we rotate 90 degrees because of the pointer instruction. We cannot go from the rightmost edge. We go through the leftmost pixel of the edge. So we select this one always. We do the push of 2 because there are 2 entrances to this function. But we are still on using the leftmost pixel of the edge, so we're still fine. We move through this selection. We do the pointer here, which means if we are not greater than 2, we rotate and we go through this strip. And yeah, the entrance doesn't have a fixed color because each entrance is based on the previous color. That makes sense. A bit jarring. I was expecting all of those entrances to have the same starting color, but it's fine that they don't. And then when we continue forward, we do push subtract. Therefore, if we were going to address 3, if it's not greater than 2, we rotate and we do this selection. If it's greater than 2, we do -2 and we continue to the next one with this here to explicitly guarantee that we are going through, which actually we don't even need. I might just remove this black pixel here because that's not needed. Okay, so that should be everything that we need, which means it's time to try to generate an image and see if the Piètre interpreter is able to run it. Trying to do Fibonacci is going to be complicated, so maybe let's try something simpler. Let's try just our function selection process. let's try something where the first function has, let's say, 4 entrances. It has the first one, in which we just do a push int. So if it has 4 entrances, then the first entrance of the second function is going to be 5. And then we return, so we leave the current function. We go back to the selection with the stack having the address we're going to on top. And then we do a bunch of entrances that are useless. Just because I want to try with more than 2. I guess just trying with 2 is fine. Let's try with 2. So it's going to be going to address 3 afterwards. And the entrance here has just the terminate. So our main calls the second function, has a return point, and terminates, basically. And to have a return address, we need to push the return address on the stack as well, which we're going to do with pushing 2. Okay. Function 1 is going to have 1 entrance to test with only 1, I guess. And what is it going to do? It's going to do... I have no idea what to do. Out character, which I think takes an int. Oh, no, just whatever is on the stack. So if I push car 42, push int 42 out character, push int 10 out character return. I think the out thing consumes the stack, so I don't have to pop afterwards. Pops, yeah. And let me just check. I have a moment of doubt. Yes, it is 10. So push 42, print, push 10, print, return. Okay, let's look at what this would look like. That's a much smaller thing. What is this big value? Okay, that's probably the... Oh, I still seem to have some kind of debugging thing. I would need to fix that. That's the 42, yes. Now it's taking a bunch of space, and we have the print and then the return. That's going to use the value on the stack to go back. Okay. That should work. No, I see already something that's wrong. No, it's fine. Okay. It is fine, I think. Yes, after our entrance, we do a terminate, which means we have no instruction. I was seeing here a line here that will not be an instruction because it does nothing on its own, but that's because we have no instruction after our terminate. We just go to this thing that stops the execution. Okay, so now the last thing I need to figure out is how I print and make an image to the file with this. Okay, so now I need to remember how to write to... I do remember there was an issue where like display image worked with all image formats, but for some reason writing to a PNG required doing a conversion or something. Something we struggled with last time. Because I think last time we tried to do something. A right image of test.png of our first program. And yeah, no instance for writable. And I think it was a matter of trying to convert. And I don't remember how that works. Would that be in color space? I guess I can do a 2-image RGBA, which will convert to whatever the image is into something with double. Okay, that seems to have worked. So is there now? There is a test PNG image. Which seems to be our image. This viewer doesn't zoom properly, that's fine. If I npiet, well, what's the arguments npiet expect? Verbose, please. Show warnings, please. Trace. No, not trace, because it's super verbose, so let's only do it if needed. And yeah, let's try test. So this should print a star, a new line, and stop, basically. Is it not called test.png? Or is it just it needs the options? Okay, that seems to have worked. Let's try it with trace. So step 0, we push a 1, that's fine. Then we go all around the image, because if we go back to this, we go all around the image using the corners of the image to bounce, and we should arrive here. So we push a 1, we do a pointer, which is this one, we rotate here. Duplicate, push to greater, not pointer, that's what we were expecting. Pointer 1, so we are rotating because our value was 1, which was less than 2. We push 1, subtract, duplicate, not pointer. We enter this function. The entrance is not having all the same color is weirding me out. I'm tempted to change that. Pointer, duplicate, pointer, pointer. Okay. And push 2, which is our return address. Push 3. And then we do all the selection again. Yeah, that seems to be working. Okay, so we have generated a first image that works from bytecode. That was manually written bytecode. Our project is far from finished, but we seem to be able to generate images. That means we have finished the assembly phase. So we have done the input and the output of the most difficult part of the compiler, because now, given a source file, we're able to have the fully resolved AST. And we have something that, given the bytecode, is able to generate the output image. So the input of our compiler done, the output of our compiler done. Now the only thing that's left is all the middle part, which is the complicated part. So next time we'll start tackling the actual compilation, which will be at first AST traversal, name resolving, type checking, maybe some small optimizations, like some inlining at this, well, not inlining, but like maybe some constant propagation, that kind of stuff can be done at that point, purely as AST rewrites. And then when that's done, we'll need to do the lowering into IR. And then from that, we'll need to do generating the bytecode. So the project is far from finished, but we've done the input and the output. So that's half of what I wanted to do this evening. The other thing I wanted to do this evening is go dig into something very fun, but very... Curse isn't the right word, but it's not the wrong word. I want to go do some template Haskell. Let me just put that here and put that at scratch. There we go. Because I will want to commit this first. So we're going to add the 3 templates we've added. And our changes to assembly and to templates. Best commit message. Okay, so that's done. So now let's have a look at this. I am going to want to automate this mess. And by automate, I mean I want to, at compile time, generate all of those declarations. We are already using template Haskell in this file. This embed file, basically at compile time, we'll go look at the file pointed by this. We'll do some IO at compile time. This is fine. Read the file and insert here an expression, which is the content of the file. So basically, at the after this template Haskell phase, when we compile this file, this is a string literal, basically. Well, it's a byte string literal, but that's same thing. So what I want to do is to make something that, given the list of files in the folder, generates all of those declarations for me. I haven't done a lot of template Haskell in a while, so let's go have a look at the documentation. What I remember is this. There is a Q being for quotation, which is the one in which template Haskell runs. And what we need to output is, we have a few options. An expression, which is something that will be replaced as an expression for an expression context at compile time, or a declaration. And dec is what we want. We're going to want to return a list. We're going to, our template Haskell expression will need to return something that is a list of declarations in this Q monad. And this is going to be a bunch of value declaration with this body here. Is that correct? Or is it just... What is the pattern here? That would be just a var name. The body is going to be not guarded, so just a normal expression. And no declarations afterwards. Yeah, that's going to be something like that. So we can have a look at something I've already done for the purpose of tests, but that is slightly different. I think there is a restriction, however. I think the functions for template Haskell need to be defined in a different module from the one I'm using them in, because I need to be able to compile them first to use them in another module. So I might want to do maybe a helper module for something. Let's think about it. Okay, so I want to look at the test, because in the test I have a file called locate, where I already do this. Here's a function that returns something in the Q monad. So that is something that template Haskell understands. And what it does is just run some IO thing that basically for each file in a directory gives me a literal expression, which is the string literal of the path. So that's something that's very similar to what we're going to want to do, except not exactly. So let me actually copy this. How are we going to want to do this? I'm going to do it here in the template folder, I think. So this is going to return do I give the directory as an argument to this function? Despite the fact that it is itself in the very directory that it needs, I think yes, just because I will need to be able to, if I try to decide what the path to the current folder is, I will have to decide what is relative to. That being said, that doesn't seem too complicated. I know exactly what the suffix is, and therefore I can drop anything before. No, I think I don't need that. So list, so generate templates is gonna be something that evaluates in this quotation monad and gives me a list of declarations. So I'm gonna want to first by I'm gonna first want to run something in IO that gives me the name of the files and the corresponding. Yeah, I basically just want to create a list of the files, and from that, I can then afterwards create a list. Or is it just. Can I do it in one go, basically? Can I do something that traverses. Yeah, I can probably, rather than doing that, doing two list traversals, creating the list of files, and then doing a second thing. I can probably just do. Okay. So I will need to know the current directory. No, I need to be careful there. Because I don't know what this is gonna say at compile time. I'm not sure what this says at compile time. Well, there's only one way to know, I suppose. And I guess I could try template Haskell get current directory. Yeah, okay, apparently get current directory during a run IO in the template Haskell thing will give me the correct. Yeah, will give me the correct value. Perfect. So that gives me a file path, which I think is just a string. Okay. What I'm going to want to do is I'm going to want to figure out a way, because I still want to use the embed thing I'm already using. Is there a way? I wonder if embed file takes an absolute path. If yes, that's fine because I will be able to just give. I can try that, and if it doesn't work, we'll try to do something smarter. Okay, so we get the current directory, which is where we are. Oh, I'll need to be careful because I'm gonna be running this function from the top level files. I'll need to be adding. Okay. Okay, so we are gonna do this. List all the files in the directory, and then for each file in this thing, output a declaration basically. And that's going to be our list here. So for each file in all the files, except I probably want to do instead a sequence because I want to be in the list monad so I can do some guard. So for each file in all files, guard not is dir file. There shouldn't be any directory in there, but just in case, guard take extension of file equals .tmp, which is our template. And if that's true, then we can return the declaration that we want to have for this, which is going to be something. So let's go back to the template Haskell thing. Actually, I'm going to get the content of the file. So the expression within this is going to be the result of calling an embed file of the file. Oh, but that's going to be in the QMonad. So it's going to be in this content here. We get the content. And then here is where we output our result, which is going to be, and we go back here to the template Haskell thing. Our declaration is a value. I think it is. I think that's what it is. Yep. It takes 3 arguments. The third one is going to be an empty list. The first one is the pattern, and it's going to be a variable name, and I need to make a new name, and I don't remember how that works. And this is going to be a variable pattern with the template name that we have not created yet. And the body is going to be a normal body with the expression, which is the content. So now the template name is the last thing. Names are a weird thing. They're a way to refer to things at compile time. And I do not remember. I think there's a new name. I think this is what I want. I want to create a new name for that thing. So that variable name is going to be a new name, and the string of it is going to be, I will want to get the base name of given a file path, I will want to get the file name. Okay, so take file name will give me what I want. Drop extension will give me, drop extensions even, will give me what I want. So this is going to be drop extensions of take file name of the file plus template, which is not the same thing that we have today. So we're going to have to change every single use of our templates so far, but that's fine. It's not a lot of them. So that's the variable name, that's the content. And we return a value declaration, which has a pattern, which is just a template name, and a body, which is just the content. Will this is there a way for me to add a signature? I guess I could add a signature. Actually, our expression is not just going to be the body, because that's not what we do here. Here we do a function call of make template on the body. I guess I could add the signature, but we don't need that probably. So I will need what does this look like? This is going to look like, so the expression here is not going to be just whatever expression we already have. It's going to be a function, an application, which is going to be the function here, which is going to be the variable name and the expression. So the body here is going to be an application of function of template function and the content. And the template function is going to be, I'm going to need to do a lookup of the name. I don't know what this does. It's not very well documented. No. I had found a pretty good tutorial for template Haskell a while back, which did explain. Is it this one? I think it was this one. Names. Let me zoom this. I guess I could give it as an argument, however. Maybe that makes a lot more sense. rather than trying to figure it out, yes, I think it makes a lot more sense to just give it as an argument. So this is going to be taking a name, which is the template function, rather than trying to do a lookup based on the thing. So I can just say what function to apply. And here, I can say that the body is this thing on its own. Okay. Or I can just, I don't know, I can probably inline this by just doing something like this. There we go. Okay. And that should be everything we need. And now here, if this is correct, I should be able, instead of having all of this, I will need to import assembly templates load, which is starting to be a very long import line. And I can replace all of this stuff by, how did we call it? We called it generate templates. And I will need to give it something as an argument. And that something is make template. Because if I remember correctly, one single quote is for a type and two, got a function name, add a single quote. There we go. So this should be enough to replace all of this. Except the names will be different. Therefore, we're going to have to rewrite all of our assembly, but it's just a matter of switching names. Okay, so we need... here I have, for my tests, I have template Haskell as a dependency. I'm going to need to put that in the dependencies of the library as well. Which means I think I can remove it from the dependencies of the test because it's part of the global dependencies. Likewise for directory. And probably file path as well. Yep. What's the correct way to sort those lines? Let's see. Okay. Okay. Is dir is not a function. Okay. In locate, I had something here. Oh yeah, of course. It is the is dir is the result of doing this. Okay. Oh. Okay, so that was wrong. So this gives me only the file name. So if I want the full file path, I need to do template dir and name is dir this. I check that it's not. I checked that this file path is not a directory. I checked that taking the extension of the file name is .tmp. And then for each of them, I don't need to do the take file name because I already have just the file name. So drop extensions plus template. Okay, let's try that. Oh, and this is the file path. And name, this is the file name. Yes, of course. No instance for... Aha, yes, of course. How do I fix this? I guess then I'm not gonna do this. I'm gonna go back to what I was doing, which is doing a cat maybes of for all files, do a file name, do, and now this do block is no longer in the list monad, it is in the queue monad that we are here, which means I can run arbitrary things like this. But here I cannot do a guard, that's not gonna work. So here I need unless I return... No, because here I'm returning one element for each file, which will be a maybe of the declaration, and the cat maybes will transform that list of maybe declaration into a list of declarations. So here I need to return something which is just something if... So I can do this with a multi-way if not is... Sorry, if is dear nothing. If tech extension is different from TMP, nothing. Otherwise, we are in the case that we want, and we can return... Actually, that's not going to be a pure because I need to do more things. So those are pure nothing. And otherwise, open a do block, which is this do block. And I'm going to align it slightly differently, I think. Nah, that's fine. Eh. Okay. I'm just maybe just gonna do that so it looks a bit better. Okay. Is this better? Oh, except this needs to be in a maybe now. So it's pure just. Okay. Exception when trying to run compile time code. There we go. Huh. Oh, that's cursed. Oh, that's cursed. Okay. The get current directory is not the one in which the file is. It is the project. It is the project root. Ah. How do we fix this? Does that mean I have to hard code the location of this? That's not the end of the world, given that the location is already hard coded by this. Kinda. Let me just look at file path, because this is where we have this function here to concatenate things. Is there a way, if I have a list of paths, to combine join path? Okay, there we go. So this is going to be a join path of, so this is the project directory, I suppose. Root. And this is then gonna be the long list of all of the template path. And the template path is gonna be just a list of file path, which is going to be I don't like hard coding this. It's why I was using the get current directory in the first place. But since it's hard coded here anyway, if we ever move this file, this would have to change. So this would have to change. So I think that's fine. Okay, so we get the current directory, which is the root directory. The template directory is join path of this directory and all of this template path. Okay. Illegal variable name. Yes. The way they were named was before no longer works. Unless I can probably name them the same way if I, let's have a look at, would that be in the prelude? Would that be in string? Would that be in character? Like something that transforms a string into a string to remove, to make it into camel case, basically. Let's have a look at what's in the templates. Yeah, I guess I could just make something that, let's see. Is there a lowercase string? Yes, but that's not in the packages. I guess it's a map to lower that I want. Is there a capitalize or text transform string? There is a bunch of them, but not in the modules that I already depend on. I suppose I can just do, I guess I can just do a map to lower, or I can actually do it this way. Okay, and now variable in scope push for template, that's true, because push for template was defined as push for template is just instruction template. I'm gonna put that back. That seems to be working. Well, it seems to be working. We don't get an exception at compile time. That's maybe a bit ambitious to say it's working. Oh, I wanted to remove somewhere in the assembly. Or, yes, I have a trace. Where is that? I'm gonna need to rerun stack.ghi so that it's aware of the changes made to the packages. There we go. Okay, so I'm gonna need to re-import everything. I don't have the imports in. I don't seem to have the imports in the history. I'm surprised. I was hoping to avoid having to type them again. Oh well, so what do I need? I'm gonna need to import whatever the name of that library is. So import graphics.image. Okay, so now let's redo function 0, function 1. Our first program is this. Write image, display image, our first program as well. It should be enough to just test that everything is still working as expected. That seems to be working as expected, so that's good. That means with the new compile time templates, we still seem to be generating programs. And if we try running this, we do get the thing we were expecting. Perfect. So that means that this nonsense worked first try. I honestly did not expect that. But yeah, the big change is now instead of having a bunch of this template equals embed this file, and sometimes having the problem of like if we don't make the proper string, we'll get it wrong, we call generate templates, which is defined in this file here. And this is compile time code that, based on the root directory and the path to the template file, list all the files. And for all the ones that have the correct extension and are not directories, therefore all of our templates, we create a new declaration to add to the file, which is a value declaration where a template is, the pattern is a template name, and the body is just the result of calling the existing embed file thing, which I could probably just rewrite and not depend on, because it's probably just read the file basically. But I guess they probably do have some smart things in place to avoid errors in case the file doesn't exist. I think it's better to just keep it that way. Okay, and I think this ends all I had in mind for today, because we finished the assembly. We are able to generate working images from bytecode, and this finishes the rewrite of the template generation, because now we have just this one template Haskell call and everything is generated for us. Yeah. I guess it means next time, probably Thursday, but I might have to skip this Thursday. If that's the case, next Tuesday, we can attack the compilation proper, so name resolving, type checking, and then start moving on to lowering into IR. Okay, yeah, we've done everything else. Now what's left is the hard part. But yeah, that's gonna be, I think, all for this evening. I am pretty bad at estimating how long things are gonna take, apparently, because I thought the template Haskell thing would take longer than this. That's the wrong buffer. No. I want this one. There we go. You can go back to being Scratch. So what do we have? We have modified package to include new dependencies. That's fine. The Cabal file has been modified accordingly. That's fine. We have a new file, which is a load file. Assembly has been modified to remove the trace. I guess I can bundle. No, I'll make that a separate change. So our change here is we've removed all of those things by just the generate template. And we've added the generate template here. And there we go. And with that, I think I'm going to stop here. Thank you for tuning in. That was fun. That was faster than I thought it would be, which is always a good surprise. And that means it is time for me to go boot the remake of the original Talos Principle that was released yesterday. Have a good evening, everyone, and I'll see you either on Thursday, or on Tuesday, depending on whether I can maintain Thursday streams. Thank you for tuning in, and see you next time.